Okay, cool. So today we're going to talk about a paper that is quite old. It's about an active learning. So I think active learning has been a quite popular concept in machine learning, but like this time today we're going to take a look into one of the early papers about it. So I'm going to share my screen. Yeah, can everyone see my screen?
Yeah, it's all good, Inneke.
Okay, cool. So yeah, this paper is called Improving Generalization with Active Learning. Yeah, it is quite old, and I think this paper is, to me, is quite conceptual and a little bit philosophical. Like it's digs into the early ideas of active learning. So yeah, let's just start and we can discuss about this paper. So what is, first thing first, what is active learning? Here they make the definition of active learning is that any form of learning in which the learning program has some control over the inputs. So in other words, it's a training mechanism where the training system, we don't simply choose the examples at random, but the goal of this active learning is that we want to do efficient learning. So we want that the examples that added to the training set are the useful examples. So we want to gain something new, some new information from the new examples instead of just picking random examples that might not contribute to the learning of the models. So yeah, and basically with this active learning, we will restrict our domain where we sample our examples. So that's why it will theoretically have a lower complexity, just because we restrict the size of the domain where we sample the examples. And they also mentioned here one of the way, the simple approach to do active learning is by doing what they call selective sampling. So with this concept, basically what we want to do is that we want to determine a region of uncertainty in the hidden representation where we where the model has an uncertainty on I'm sorry, so we will divide the area in the hidden representation to say that, okay, if inside this region of uncertainty, the model might misclassify the examples. So basically we want to sample our training examples from those areas, and hence by reducing these areas of uncertainty, we will sample a better examples. Because if we sample from the area that the model is certain, there is no point, because the model will not learn anything from these examples. Anyway, please, if anyone wants to say something, give comments or ask questions, please don't hesitate to stop me. Okay, so how do they do this selective sampling? In this paper, they introduced a concept called concept learning. So essentially, concepts is, I think we can just look at the picture. So yeah, so imagine if, I imagine this is like the, in terms of in machine learning, I imagine this is the latent representation, and then we have like this boundaries that basically distinguish the example. So imagine this is a binary classification. So we have two outputs, 1 or 0. We can see here that if that example lies within the area that is bounded by this, what they call concept, then that example is is classified as 1. And if the example is outside this concept or this area, then this example is classified as 0. So I imagine this is like, this boundary is like the boundary in the hidden representation. And in this example, we see that there are a few different concepts. So
so each rectangle is essentially an allowed solution that is that could be the true solution, right?
Yeah.
So you sort of assume here that the problem space is indeed rectangular.
Yeah. That's what I understand. Yeah. Here they assume that it is rectangular, but in the reality, well, in the later part of the paper, it can be triangle or whatever shape, basically.
Sure.
And the collection of concepts they call is the class C. Basically, it's just the collection all of these possible areas or boundaries. And what is it in neural network context? So later in this paper, we will talk about actually this each concept is just like a set of hyperparameters of the model. So we want to sort of like map for each configuration that are hyperparameters of the model, like what is actually the area, the shape of the hidden representation that particular hyperparameter represents. Okay. Yeah, so this part, well, I will say, yeah, as I mentioned before, we classify a point as positive if the example lies within the bounded area, within the concept, and 0 if it's outside. And the goal actually of this problem is that we can see the statement here, but basically we want to find a concept that has the lowest error compared to the unknown target or the ground truth. So I think I say it in other words, it's just we want to find the area in the hidden representations that best describe the examples. So we imagine that we in neural networks we convert the input examples to the hidden representations, and then the goal of this concept is that we want to find the concept or the shape or like the boundary in that hidden representation that best describe this classification. So it's like, I imagine it's like a discriminative classifier, and we want to find those boundaries that classifies these examples. And if we imagine that there are different concepts, that each concept represents different hyperparameters or different configuration of the models, then we can see in this figure two that we have areas that not all of the concepts agree with each other. So in these white areas, when all the examples are 0, all of the concepts, meaning all of the configuration of the models, agree that the examples is classified as 0. And for the intersection, for all of the concept, like all of the concept will agree that all examples that lie in that area will be classified as 1. But what happens with the area in between, like this in this shaded area, some concepts will classify the examples as 1, but then some other concepts will classify as 0. So there are disagreement other concepts. And this is what they refer as the region of uncertainty, or in this paper, the symbol is RSM. So this region of uncertainty, or in other words, is this, this shaded area is where we want to sample our examples for the next training from. Because imagine if we sample from the white areas, where all of the concepts agree that the point is classified as 0, or if we sample from the inner area, the intersection where all of the concepts agree that the examples are classified as 1, there is no point of that it will give no extra information to the model, because all of the concepts agree with each other already. So what we want is that we want to sample examples from this shaded area, and we want to reduce this shaded area or the region of uncertainty. So that is the idea of this selective sampling. And yeah, and then they mentioned here, so this shaded area, or alpha, is the probability that an example belongs to this, lies within this shaded area, is the probability that a new point from the distribution where we will sample our examples from will reduce the uncertainty. So imagine if we just do random sampling, just do the naive approach, when we will reach a point that when we keep sampling, then it will just sample from outside this shaded area, so that will be inefficient. So what we want to do is that for each step in the training, we want to recalculate this shaded area, and then we want to sample from this shaded area for the next training. So that's the iterative process. That okay, we find this, we found this shaded area, we sample from this, and then we recalculate the shaded area, and then we will sample the next examples from the new shaded area. We don't want to sample from randomly, because it will just randomly sample from the white area, which is useless.
Inneke, there's a question in the chat.
Oh, sorry, I didn't see. Is it that if there is conflict in classification, the region is uncertain? Yeah, what I understand, please anyone please feel free to say their opinion. What I understand, yes, is that if I imagine in the case of neural network, if we have different configuration or different parameters and they don't agree, like they disagree, then the point lies within
I
this.
think the point here is that this is sort of a toy problem. The authors, I think, specifically said there's no noise. So a point is either in or out, but there is no Bayesian error around that like decision boundaries. But what I would ask is the sampling from the gray area, right? One would still think that sampling from that is also not or could also be optimized, right? Because I would imagine where many more of these lines are close to each other, if I take a point from that, I would probably decrease my future sampling space more than if I would only sample, say, at the outer boundary of this gray area.
Sorry, what do you mean? It's like if
you know the figure, if you go to the figure, right? So we have this strange gray area that is essentially our new sampling space for this active learning, right? So we, as you said, we sample from it, and any new information we get essentially reduces our gray area, and we have actually learned something. Right? Now, one might ask, are all these points equal, or would it be more efficient learning by learning, say, somewhere halfway between the middle, or halfway between the 0 and the 1, because there I essentially discriminate between more different solutions than, say, at the outer boundary of very close to the 0 or the 1.
Okay, I think, yeah, that's a good point, Arvid. I don't think they mentioned about this here. I think they just like assume this is like has the same.
Yeah. So they just say sample randomly from all the gray area, and you still have the big improvement, right? Because you don't sample the white area, so it's fine.
Yeah, I think that's the improvement. Cool. So
sorry, Mahid, ask another. It's a problem definition. The problem itself is said to be without noise. I don't think it has anything to do with the hyperparameter of the model.
yeah, I think they mentioned something. Well, later in the paper, we can see is that they change this configuration of or the hyperparameters. But I think what I understand is that there is no noise. It's just we assume that it's like there are when an example classified as 0, it's real 0. It's it's not like
Precisely.
Yeah, it's not like ambiguous classification. Like when I mean when I will say like there is not like uncertainty in that classification because of the data is ambiguous, like it has like aleatoric, something like that. So it's just like when it's 0, it's 0. That's how I mentioned. But okay, we can go back to that later. Yeah, so another concept that they mentioned here is that they divide this operation as two. First is that they will draw the unclassified example from the distribution, and then we'll check the classification of that point. And they will do it in batches, just because imagine if we do it for every single example, not in batches, then we need to recalculate the shaded array every time, and it will be computationally expensive. Okay, the next section is that basically they mentioned that if we only want to have like a precise concepts that will be intractable problem, so they do approximations of this concept areas. So we'll have the superset of the region of uncertainty, which basically, if we sample inside the superset, we are sure that we are sure that the points are the point of interest or the points that are useful for our active learning, but there is possibility that the points we sample from the superset is not useful because they will cover more examples than the actual useful examples. And on the other hand, we also have the subset of the region of uncertainty, which means that we are sure that all examples that we sample from that area are in our interest, or in other words, the examples that we want in our active learning. But there is a risk of oversampling because those examples will not represent the whole. Sorry, those region of uncertainty does not represent the whole actual region of uncertainty. So if we sample too much from that example, we might disregard the other part of the region of uncertainty. So the idea is that the whole idea of this paper is that we want to have two different networks that approximate this superset and the subset. The idea is that if we sample, they mention it somewhere. Basically, the idea is that we want to, like, for example, if if we sample an example and then we see that this example is not useful, then we can reduce the supersets. So this is how like we want to find the balance between the superset and the subset by like reducing the area of superset or increasing the area of the subset. And I think they mentioned it somewhere. But okay, we just go back if we found it. Yeah. Yeah, and this is what I mentioned before, is that here they use this terminology that when they mention architecture is the parameters of the models that do not change during the training, and configuration is the network parameters that do change during the training. So it's, for example, the weights. Okay, yeah, maybe like I might have created some misunderstanding, like this configuration is actually the weights, not necessarily the hyperparameters, because if we don't change, for example, the activation function, then it's considered as architecture, not the configuration. Yeah, I think that's the point, Arvid, you pointed out, or you say something?
No, I think good.
Yep, so the concept class C is basically all the configurations or in other words, the network parameters that the network can take on this. So yeah, imagine as I mentioned, like the concept, one concept is actually 30 something. Oh yeah, I'm just seeing the chat, sorry. So yeah, the network, the each configuration of the network actually is the representation of each concept. So yeah, in imagine, because one concept, like one configuration represent one concept, actually the like this bounded area, this concept, it can only measure one configuration. So but actually we want to find the concept for, like we want to measure the uncertainty for all of the concepts, like for example here. And what they mention here is that this backpropagation algorithm, which usually is just the basic concept of how neural network learns, is that they mention basically during this I think during this backpropagation is just basically we want to find the, I will say this is like a very classic way to describe how neural network works, because yeah, of course, in like in training neural networks, we want to find the best representation of the examples in the hidden representation, and basically want to find the best concept. So in my opinion, this part is just saying, like reinforcing how actually neural networks learn.
When they were new back then, right? So it's
Yeah.
1995. It was cutting edge by at least within the decade, cutting edge, right? So.
Yeah, exactly. I was thinking, because oh yeah, this is old paper. Back then, it's just like, you know, it's just written differently, but actually it's the same thing.
You didn't have Coursera also back then.
Yeah, this is something that I wanted to say earlier. So basically, if we have, remember, we have approximations of the subset, the approximation of the concept, which is the superset and the subset. So in this case, S represent the most specific concept, which is the, or in other words, the subset, and G is the more general concept, which in other words is the superset, basically we want to find the area between that. So we will bound our search between the superset and the subset. And then if we find an example that is classified as 1 or positive between that superset and subset, then we can say, hey, meaning that your subset can grow larger, because remember, subsets might not cover the whole region of uncertainty, or might not cover the whole real concept, because S is the approximation in terms of subset. So if an instance example is positive, that means that we need to make S larger, or if an example is negative, it means that we need to reduce the G, which is the superset. So we want to find the balance between these two, superset and subset, and hence we can find the most optimum area in the domain where we can sample our examples from. Okay, and how do they implement this? So first, they divided this into two different networks. Like one network represents the subset, and then the other network represents the superset. And basically, here they mention about fighting with the inductive bias, which I'm not 100%, like I don't 100% understand this part, but like I kind of got the general idea of it. So it's like, because we know in neural network, we often introduce inductive bias that will make the network tend to like understand certain areas of the hidden representation better. Like so this can create I mean this can introduce a subset, because like I mean theoretically inductive bias is introduced to help the models learn. But then imagine if we introduce too much inductive bias, then actually the model might not be able to learn something outside this this bias, just because inductive bias will restrict the area where the model can learn from. So what like this idea they introduced here is that they want to add a new inductive bias that sort of like balance out this phenomenon. So the idea is that we want to draw a new unclassified point from our distribution, and then we just say that okay, this point we will label them as negative, or in other words, we will treat this new unclassified points that we just sample from the distribution as background examples. So imagine here, like we have, in this picture, we have like examples that we treat as background examples, and like how to say, like basically we want to find, like by introducing this background examples, then we want to learn which areas in this new in this representation that's like that all of examples within those areas like must be one. So we want to maximize the precision of this concept. So imagine here, that's why like this shape of concept is like it will maximize the precision of that. We want that all examples inside this concept to be 1. But remember that if we, because the background examples are obtained by drawing unclassified examples from the distribution, and then we label them as negative, the possible issues is that the background examples might dominate over this other examples, and the model cannot learn because it will just like everything will be background examples, and then we cannot, the models, the network cannot learn an area that covers the region where all the examples are 1. So basically, like they.
One question. Why do we actually think that networks, or why is the network architecture here so special, right? Because I'm thinking this, for when I look at the pictures, right? It's a very geometric problem. One would almost think that something like a kernel or nearest neighbor classifier would sort of do the similar thing, right? Because if you have all your points, around each point you could write a bubble or a ball that says, okay, everything around this point we believe is either 0 or the other one we believe is 1. And where these two sets of bubbles start clashing, that would be where you're uncertain, and you would sample from that. Wouldn't that be the more natural choice of looking at this?
Yeah, I agree. Well, I imagine is that actually this, like how we will describe this region can be, as you said, can be just like the kernel or any kernel. I think in this paper they approach it as the configuration, because it's like one configuration, one set of configuration might learn different shape of the region. But I would agree that it's in KNN, or it can just any kernel or like radial basis kernel, or like basically any kernel. So I think it's just like
because kernels might even be sort of better because you can tell where how far a point is from kernel boundaries, and that might actually inform your sampling a bit more. No, never mind, sorry.
Yeah, I agree. Thank you. So yeah, so with this idea of adding the background examples to try to learn these concepts, and there is this possible issues that the background examples may be too much or like dominate over the other examples. Hence, it will make the models or the network hard to learn and can generalize. They separate different learning rates for the training examples and the background examples. So yeah, as I mentioned here, we will just look at these steps. So we start with just random initialization of the concepts, or in other words, random initialization of the model weights, and then we find we calculate the squared error, basically the error of the classification of the examples with the model, and then we select, we pick, we sample the next training example, and then we want to find and then we calculate the error, and then we want to find a new background learning rate here, that basically the so yeah, this is the background learning rate. That's, there is this constant here. In the later parts of the paper, they mentioned that they pick 0.75, if I'm not mistaken. So yeah, basically, ideally is that we want to vary this constant, but it might be computationally hard. So they will just pick like one constant between 0 to 1. And yeah, we want to find a new background learning rate. So we want to balance out how the network learns with this both training and the background examples. Yeah, this is what I mentioned, is that we want this background learning rate to be enough for the model to learn from this background, but we don't want it to be too high that the background example will dominate over the training examples. Yeah, that is how they find the subset concept, because yeah, imagine in this, back to this picture, we can find like a very specific, very limited area of in the very limited area that will cover all of the examples that are classified as one. But on the other hand, we also want to find the general network or the superset, which means that in this case, the mechanism is a little bit different. It's just we want to classify the sample points from the distribution as positive instead of negative. So that way, we will end up with the area that is larger, that will cover more examples. Like we will maximize the recall of that. Well, in the subset, we'll maximize the precision. Okay. Yeah, I think this is the last part of the architecture, is that they implement it using this what they call SGNet. So basically, they split this into two different neural networks, and then they merge it to balance out between this subset and the superset. So yeah, the idea is that if we want to sample from the areas that it contain in between S and G, that they represent as S delta G here in this paper. Yeah, basically that's it. And then they they also mentioned that because again they want to, like, the constraint is that if we only sample one single example in each iteration, means that there will be a lot of computational resources required. So they want to do it in batches, and I think they will mention it, the results in the experiment results. So here they implement this experiment, this network in 3 different problems. The first one, here they simply like compares this SG network with the naive learning approach, and they compare how the concept is learned by the SG network compared to this naive approach. And yeah, basically the real concept, the real boundary is this triangles, and the right picture represents the SG network, and the left one represents the naive approach. So yeah, basically here they just like present that with this active learning, they have like a better shape. They have, it's just like they basically the shape follows like better shape, like represents the better triangle shape.
So do the different heads do they have different loss functions attached to them, or I must have missed that a bit? Because ultimately we have 2 classifiers we're trying to train at the same time, right?
Yeah.
And both of them we would expect to train for recall. because if you train them for precision, they would, squeeze up too tight. But we want to have higher recall on them so that they spread out and possibly can clash. But how is that managed?
I think like what I understand is that one for the subset, for the subset network, the S1, they want to maximize the precision, because imagine they want to have like all the examples within that concept as one, where the other network, which is G, the general one, we want to maximize the recall. Like basically we want to cover more examples than just only one. They didn't really mention here whether they have the same loss functions or not, so I don't think they make it different. I would say like actually they didn't really elaborate on how the training mechanism work. Is they just like mentioned that they have these two separate network that in the end they merge this inputs of the network. They didn't really mention how, except that how we vary learning rate. So I don't think they play
No, but the precision is actually the right word here, right? They actually trained to be very precise on the few points that they're known guaranteed, which works here because there's no noise whatsoever. Yeah.
You mean like both of them precision or what?
Yes.
Is it like,
right? So they're trained to give the correct label exactly on the points that are known. And I would feel that there's a bit of option of how each head is behaving away from the points that are precisely classified, right? So I would almost think that there is where you could tune with some hyperparameters of the loss, perhaps how quickly, for example, your certainty drops off away from the points, but I don't know what they're doing here. It's because they focus very much on the back propagation, but rather on the higher level loss that.
Yeah, I agree. Yeah, like they didn't elaborate much on it. I also mentioned like one is the precision and one is like they maximize the recall, and they want to find the balance between the precision and recall by combining them both. But yeah, I'm not clear either like how exactly they will combine on like or integrate it. Anyway, so well, the second experiment is like instead of visualizing the concepts learned, they've used this 25-bit real value thresholds. Well, I'm not really clear like what they mean by threshold. Is it like the threshold of the probability written by the model, written by the network?
Wasn't that for the choice of whether you want to sample from a point or not? If because you don't have, because you have a continuous output, you have to say at some point, oh yeah, here the model is reasonably certain. So of course there's a bit of a trade-off there as well, right? If you make this threshold such that you exclude points from sampling, even though you might actually not 100% sure about them, you risk learning a suboptimal decision boundary.
Okay, so yeah, they plot the random sampling and the selective sampling, and yeah, show that with the selective sampling the error will drop steeper, which of course it's just like okay. The last one, like I think this very minor one, they use it on the analysis of a power system. because they mention here like the idea why in what cases this active learning, or I mean this selective sampling useful, is that when the cost of drawing the samples from the probability is lower than the cost of running the prediction. So yeah, and other examples they mentioned earlier is that, for example, in NLP cases where we have a plenty labeled examples, but then the prediction will be more costly because maybe the network size is huge. So basically we want to, that's why we want when we train the model, we want to minimize the amount of the prediction, or minimize the amount of prediction, and we want it's okay to sample as much as possible, something like that. So the idea is that I'm not really clear either on these experiments, to be honest. Like they mentioned a lot, they explained a lot the ideas about these concepts, the backprop, that, but then when it comes to these experiments and the integration of SG network, I personally find the explanation in this paper is too little.
Yeah, it's early stages, so there was maybe more about getting the idea out and see what people can do with it.
Yeah. Okay. Last part of the paper is the limitations of these ideas. As we expect, is that in this paper the concepts is just either triangle or rectangular, which is quite simple. But imagine if it's a complicated concept, it will be difficult to learn. And also, because imagine for the constraint between the subset and superset is that in the subset we will have oversampling problem, and for the superset we might have concept that is too large that basically contains everything, not only useful examples. So when the concepts classes are complicated to learn, then there is a chance that the superset will just contain everything. So that's one of the limitation. And the other theoretical limitation is that if we have related to the practical limitation is that imagine if we have a complicated concepts, and then even though we want to minimize this region of uncertainty, they might still be very large, just because it will be hard for the model to learn. Like we might need a bigger network, more complicated network to learn that. Here they say we might need a lot of hidden units, or maybe we need to have a lot of hidden layers as well. So basically I think the limit is just what they want to say here is it is applicable only when the concept is easy to learn, and will be very difficult if it will just computation intractable if we need large models just to learn these concepts. So I think that's all from this paper. We have 6 minutes left. Anyone else wants to say something?
It looks like we're having a troll on the chat.
Inneke, can you please remove this troll, because I'm not an admin.
Oh, you're not panelist. Are you new finalist? Oh, sorry. It's Arvid who's finalist.
Yeah, I can't do it either because I'm not host, I think.
Yeah, only host can do it. Can you just block this
I mean,
idiot from forever.
More like next time.
It's not in attendance.
Weird. Anyhow, thank you very much for the talk. It was very interesting. I have to drop for next meeting, but it was brilliant.
Thank you, Arvid, and anyone else. If no one else wants to say something, then I will stop sharing my screen. I will stop recording.